প্রেজেন্ট করব? আমি প্রেজেন্ট করার কোনো বাটন পাচ্ছি না কেন? ওকে, here it is. I find it.
হ্যাঁ স্যার, প্রেজেন্ট হয়েছে।
Somehow it's not clear here. To avoid mirroring, don't share your entire screen or browse windows. Share just a tab of a different window instead.
Good afternoon, dear participants. We are going to start our webinar within a couple of minutes. Thank you.
So, Angshuman, can you see my slides?
Not yet. Yes, yes. Now it is visible. Just go to sir presentation mode, sir.
No presentation mode, then I can't find anyone else. How can I do it? Fix that?
You can say go to sir kind of from the beginning. Extreme left there is a option that is from the beginning, or at the bottom you can find it.
No, I mean, is there is an option that while presenting I can see the participant?
I think no.
That is not possible, right?
Mm-hmm.
Okay, but I think there is an option for that. Maybe not. So can you see my slide now?
Yes, sir.
Okay, so everything looks good, right? Resolution and the
Yes,
presentation.
yes,
Yeah.
yes.
Only thing is I can't see myself, neither anybody, any participant. So if there is if anything goes wrong, then please let me know.
Yes, sir.
Yeah. Actually, there is an option that where while presenting you can see the participant. I just can't figure this out how it is. There are possibilities to do it.
Hello, am I audible? Someone, hello, am I audible? Hello,
তাপস দা ইকো হচ্ছে।
Eco.
sir. Sir, are you with us, sir?
Yes, yes.
Principal, sir.
Yes, yes,
Okay.
yes, yes.
Yeah. I'm
Okay. Actually, I left the meeting due to some network issues. Okay, good afternoon, everybody. Today we have Professor Joyram Guin with us. And before we start our program, I would like to request our principal, Honorable Dr. Devnarayan Roy, to deliver his welcome address. Sir, please.
Good afternoon to all. Respected Joyram Guin, School of Chemical Science,
Hello.
Indian Association for Cultivation of Science, respected principals of different colleges, respected officer in charges of different colleges, other dignitaries, academic luminaries, esteemed colleagues from different institutions, my dear students, ladies and gentlemen. On behalf of the Office of the Principal, Teachers Council, Internal Quality Assurance Cell, non-teaching staff, Student Council, and also on my personal behalf, I heartily welcome you in this webinar at Jhargram Raj College. The Jhargram Raj College started its journey as Jhargram Agricultural College in the year 1949. The government of West Bengal took over the college in 1953 and was affiliated to University of Calcutta. In the year 1985, Vidyasagar University took its affiliation. Now the college celebrated its golden jubilee in the year 1999. Presently, Jhargram Raj College is one of the most prestigious institutions in the district of Jhargram, which engages in educating the first generation of learners from the socially and economically backward community and from the tribal families. There are a total of 15 departments in humanities, science, and commerce disciplines. The Department of Chemistry, Zoology, and Bengali offer postgraduate degrees since 2005. There are also two boys' hostels and one separate girls' hostel, making our college a partially residential campus. The college as a whole caters more than 3,000 students. A large number of UG students are able to secure first class in the university examination, and a quite few number of students qualify JAM and other national level competitive examinations to pursue their masters in various national institutes of repute in every year. Almost 90 to 95% of the postgraduate students secure first class marks in their qualifying examination, and many of them qualify NET, SET or equivalent examination for pursuing their research work as well as also for lecturership. In the year 2019, our college came under prestigious DBT Star College scheme sponsored by Department of Biotechnology, Government of India. In the year 2020, we achieved Educational Excellence Award conferred by G24 Ghanta, and in the same year, we get another honor to extend more than 4,000 online courses to 3,000 enrolled participants through Coursera organization of USA at free of cost with pass-out certificate. Our chemistry department, marked as one of the best departments in the state, the diversity of scientific opportunities that now exist at Jhargram Raj College has grown out of a long and distinguished tradition of chemistry teaching and research. It is one of the reputed and one of the oldest departments of the West Bengal. In the year 2005, we have started post-graduation course. Jhargram Raj College graduates, along with many other successful persons who spent their formative years here, have gone on to make extraordinary contributions to the science as scientists, researchers, teachers, intellectual leaders all over the country as well as on international platforms. It is a great moment for me that our postgraduate Department of Chemistry of Jhargram Raj College is going to organize DBT Star College Scheme sponsored a series of national and international webinars. The title of today's webinar is Concept of Chirality and Asymmetric Organocatalysis. This is the fifth program of Department of Chemistry in this year, and during the lockdown period since 2020, we have organizing already 41 webinars, 2 value-added courses, and 1 summer school. We hope this webinar is very much pertinent to present situation. Actually, we do not know after how many days we will able to overcome the present pandemic situation of COVID. We also do not know after how many days the normalcy begin in our society. I hope the deliberation of our honorable speakers are not only enrich our knowledge, but also boost up the mental strength of our participants. So far my knowledge concerned, last but not the least, our honorable speaker, Dr. Joyram Guin, is very energetic, enthusiastic, dynamic, soft-spoken person, engaged in various activities in the domain of academic atmosphere. He did a lot of outstanding work in the field of chemistry. With this, I once express my heartfelt gratitude to our honorable speakers and also distinguished delegates for sparing their invaluable time with us. I wish a grand success of the program. Thank you very much. আজকের এই সভায় উপস্থিত মাননীয় আজকে আমাদের যিনি বক্তা ডক্টর জয়রাম গুই ছাড়াও আমাদের বিভিন্ন সরকারি এবং সরকারি অনুদান প্রাপ্ত কলেজ থেকে আগত বিভিন্ন অধ্যাপক অধ্যাপিকা বৃন্দ, শ্রদ্ধেয় বিভিন্ন কলেজের প্রিন্সিপাল, অফিসার ইনচার্জ, টিচার ইনচার্জ, অন্যান্য প্রশাসনিক আধিকারিক বৃন্দ এবং আমার স্নেহের ছাত্রছাত্রীরা, সকলকে কলেজের পক্ষ থেকে যথাযোগ্য স্থানে আমার আন্তরিক শ্রদ্ধা, প্রণাম, প্রীতি, শুভেচ্ছা, ভালোবাসা জানাই। এই কোভিড সিচুয়েশনের মধ্যে আমরা চেষ্টা করছি মাঝে মাঝেই এই ধরনের আন্তর্জালিক আলোচনা চক্রের মাধ্যমে আমাদের ছাত্রছাত্রীদের কাছে পৌঁছে যাওয়ার, এবং আমাদের রসায়নবিদ্যা বিভাগ থেকেও অধ্যাপক অধ্যাপিকারা চেষ্টা করেছেন যে দেশে বিদেশে বিভিন্ন প্রান্তের বিভিন্ন জ্ঞানী গুণী মানুষ তারা এসে যাতে আমাদের এখানে ছাত্রদের সামনে বলেন। আমরা তো অনলাইনে ক্লাস নিচ্ছি, চেষ্টা করছি যতটুকু পড়ানো, কিন্তু এটা আপনারা সবাই বোঝেন বা ছাত্ররাও বোঝে যে একটা অনলাইনে ক্লাস আর একটা ক্লাসের মধ্যে বসে ক্লাস, দুটোর মধ্যে অনেকটাই তফাৎ থাকে, অনেকটাই দূরত্ব থেকে যায়, অনেকটা আন্তরিকতার অভাব থেকে যায়, এবং শুধু তাই নয়, সুনির্দিষ্ট সময়ের মধ্যেই সেই ক্লাসগুলোকে শেষ করতে হয়, কারণ এখানেও স্মার্টফোনের একটা ডেটার ফ্যাক্টর থাকে, বা প্রত্যন্ত জঙ্গলমহল এলাকার বহু ছাত্রছাত্রী দরিদ্র পরিবারের, তাদের সেখানে সেই পরিমাণ, সবাইকার ক্ষেত্রে স্মার্টফোন নেই, কারুর ক্ষেত্রে ইন্টারনেটের সমস্যা থাকে, তবুও তার মধ্যে তারা কষ্ট করে পড়াশোনা চালিয়ে যাচ্ছে। আর আজকে যারা আপনারা এসছেন বক্তা তথা যে বিশিষ্টজনেরা এসছেন, তাদের কাছে আমরা সত্যিই কৃতজ্ঞ। আমি ব্যক্তিগতভাবে ঋণী, আমাদের আবেদনে আপনারা সাড়া দিয়ে এসেছেন। আমরা চেষ্টা করছি যে এই রকম ছোট্ট ছোট্ট সময় উপযোগী এবং ছাত্রদের আংশিকভাবেও যাতে তাদের কাছে পৌঁছানো যায়, তাই বিভিন্ন জ্ঞানীগুণী মানুষের বক্তব্য তাদের সামনে আনার চেষ্টা করছি। এই কোভিড পরিস্থিতিতে আপনারা সকলেই সুস্থ থাকুন, সকলেই কোভিড বিধি মেনে চলুন, এবং মাস্ক অবশ্যই পরুন। যাদের যাদের এখনো টিকা হয়নি অবশ্যই টিকা নিন। যদিও আমরা জানছি যে বর্তমানে কোভিডের যে নতুন স্ট্রেন, যে ডেল্টা স্ট্রেনের কথা বলছে, এবং এটা আমরা কয়েকদিন আগেও আমাদের এখানে একটা বক্তৃতাতে আমরা দেখেছি যে ডেল্টা স্ট্রেনের যে জিন সিকোয়েন্স সেটা পুরোটাই পাল্টে গেছে। অর্থাৎ প্রথম যে করোনা, তার যে mRNA যা স্ট্রাকচার ছিল তার মিউটেশন হতে হতে, এবং তার যে এই যে প্রোটিনের কথা বলা হচ্ছে, তার যে সারফেসে যে প্রোটিন রয়েছে, এই প্রোটিনগুলো স্ট্রাকচার এত দ্রুত সে পাল্টাতে পেরেছে যে বর্তমানে সে এখনো ভয়াবহ হয়েই রয়েছে। তাই আমরা চেষ্টা করব এই আমাদের যতটুকু সংক্ষিপ্ত জ্ঞান, যারা আমরা পড়াশোনার জগতে রয়েছি, সেই জ্ঞানের উপর ভিত্তি করেই গ্রামাঞ্চলে দূর দূরান্তে প্রান্তের মানুষদিকে সচেতন করা। অকারণে ভিড় জটলা থেকে দূরে থাকুন। যদিও মানুষের রুজি রোজগারের একটা বড় সংকট দেখা দিয়েছে, এটা আমরা জানি, তবুও যতটা তাড়াতাড়ি সমাজ সুস্থ হয় এই আশা রেখে সকলের সুস্থতা এবং দীর্ঘায়ু কামনা করে আজকের অনুষ্ঠানের শুভ সূচনা করছি, এবং এই অনুষ্ঠানের সর্বাঙ্গীন সাফল্য কামনা করছি। সবাই ভালো থাকুন। ধন্যবাদ, নমস্কার।
Thank you, sir, for your nice welcome address. And it is a really great moment for us because we have not only the participant from our college and also neighboring college of our own college, and we have participants from various institutions both across India and also within our country. So that's feel us, very good. So now, as a coordinator of this team, I would like to introduce Professor Joyram Guin. Professor Guin now presently acting as a professor of School of Chemical Sciences, ISCS, Kolkata. Professor Guin did his BSc from Calcutta University in the year 2002. He did his master's from IIT Kharagpur in the year 2004. He did his PhD from the International Graduate School of Chemistry, West Felice Wilson University, Munster, German. He did his first postdoc from University of Geneva, Switzerland during the year 2008 to 2010 as Humboldt Fellow. He did his second postdoc from Max Planck Institute for Kohlen-Forsang as a Max Planck Fellow, and after that, he joined as an assistant professor in the Department of Organic Chemistry in ISCS in 2013. After that, he became the full professor in the same institute during the year 2019. Professor Guin published more than 40 research articles in various international journals. He has guided 4 PhD students and 1 postdoc, and 10 PhD students and postdocs are now working under his laboratory. Professor Guin delivered many invited lectures in various colleges, IIT, and also various research institutions globally. He also fond of to deliver popular lecture for the popularizing science education in general and chemical science in particular across India. Professor Guin awarded Associate of Indian Academy of Sciences in 2019, Theme Chemistry Journal Award in 2014, Best Student Award from the IIT Kharagpur during the year 2003, and he received National Scholarship in 2002. With this brief introduction, I would like to welcome Dr. Guin to deliver his talk. Please, sir.
Thank you very much, Taposh, for kind of introduction. And I think my voice is okay. Everybody is audible to me.
Yes, is audible.
Okay. So again, thank you very much for the invitation. I really love to talk this kind of topic, which is more like a basic chemistry, and then later on we touch upon a little bit about our own chemistry. I'm preparing this lecture, particularly in the focusing of the graduate students who just now in touch with the flavor of what is basically the chirality and the asymmetric synthesis, particularly organocatalysis. So if it is not a pandemic situation, I would have loved to go to you and interact with the students personally, which I really love it. But anyway, I mean, we all can't do it at this moment. So let's proceed with that, with this mode of presentation. And as it is shown in my slides, that I'm going to talk about chirality, and of course, later on asymmetric. So when you talk about chirality, then we talk about the molecules, right? So I mean, I always start this kind of presentation throwing a questions to the students. So this slide is particularly for the students. So please have a look all this molecule carefully and think about which of them are chiral. You know what is chirality, what is the concept, and all those things right now. So just think about it, whether these molecules are chiral at all, or none of them are chiral. So I leave this to you. So these are the very simple molecules I think you come across very often when you teach with organic chemistry, any textbook. And let's think about it. So this is the question I throw to you. And I hope, I think some of you think these are chiral, some of them are not. So this kind of confusion is still there. I hope after this lecture, you will realize what is actually. Okay, so let's begin with that. So I always go through the fresh start from the morning. So how do you start it? Of course, we take a milk in any different form. It could be coffee, it could be tea, it's just a milk, or maybe paneer, cheese, butter, whatever it is. But these are the lactose. And what is important, that this molecule is a chiral entity, right? So that means we are eating chiral material. Similarly, the sucrose. is a sugar. This is also chiral material. It's not only chiral material. What is interesting, this is the one sense of chirality is there. So the nature producing material with a one sense of chirality, so it's an extremely enantiomer pure material. So that is fascinating. Similarly, if we take a everyday carbohydrate food, some of you don't like it because nowadays we are a bit conscious about the carbohydrate uptake, but anyway, we need to do it. And in all cases, you find that this kind of three-dimensional structure networking is nicely arranged, and there is a lot of stereogenic center or chiral centers. And these molecules are absolutely enantiomer enriched. So this is fascinating. So everywhere we
Sir,
find the
sorry to
chirality.
disturb, your voice is very low, sir.
My voice is low?
Yes, yes, sir.
Okay. Let me.
Can we increase the volume?
How about now?
Yes, now it is audible.
It's okay.
Okay, okay.
So this much volume is okay, or should I increase again?
Little bit more, sir.
Now?
Bit more.
Is it okay?
Now I think it is audible, sir.
Okay, great then. Okay, so let's continue. So my slide is visible now. Hello.
Yes, visible, sir. Please continue, sir.
Okay, great. So I was talking about that every day we encounter with a lot of chiral molecules or enantiomer-enriched materials that nature produce, and some of them we also prepare. Synthetic. So you know this kind of structure. I think in any kind of bioorganic chemistry or you find this kind of structure. So these are protein. Some of them are enzyme with the cofactor, the protein. So and this is what is the building block is obviously the peptide. So is the amino acid linkage. And the amino acid, most of the amino acids are having stereogenic center. And that means this is the enantiomer material, and our body is made of this kind of things. And this is the amino acid, and we all know that if you have a 4 different hand, then it's a chiral molecule. I will come in a minute, and I'll show you what is the meaning of these 4 different hands. And of course, again, you know the DNA structure, which is the building block of our life system, and this is also nicely arranged. It's a helical structure, so that also shows the chirality, right? So, and these are the molecules, some of them nature produce, and we also prepare in the lab. So these are the drug entity, and we need to consume them when our body gets sick. And as you can see, this is also contains stereogenic centers. So that means all these slides give you a flavor that we are basically surrounded with the chiral materials. So we must know what is chirality. We must know from where it comes from, and we must know how to prepare it, how to control the enantiomer selectivity. This is absolutely necessary in modern science. I mean, it was before as well, but now it's really evolved in a different way. And look at these molecules. This is the Taxol, and just look at the stereogenic center. How many stereogenic centers are there? It's a tremendous, right? And nature produce only one enantiomer of it, and this is excellent, right? So indeed, there is a need, but not the laboratory. Look, if you just go outside the laboratory, you find this kind of arrangement on your garden. You obviously find these things. So see, these are the nice, again, helical structure. And all these cases, even we are so fascinated with the chiral entity, we start to making our building. So like is a helical stair, is a helical building, and basically chirality is everywhere. And indeed, it's not on the planet, it's even on the space. It is known that you can find this kind of entity. So this is basically propylene oxide. It's just only one, it's a racemic. Both of them are there. So the chiral molecules, it's in the space, it's in the the planet, in your body, it's almost everywhere. So then the question is, from where this concept come from? Who actually started? Let's go a little bit backward and go look into the history of this one. So this is, every phenomena, every concept is developed based on the certain observation. And this is the observation. The observation was the what realized the sum of the organic molecules has ability to rotate plane polarized light. I'm sure you all know what is plane polarized light. So this is the light source, and it's passing light all over the direction, and then you put a polarizer. So polarizer basically allows light to move in a particular direction, and now this is the plane polarized light. And then if you bring the sample, some of the organic or even inorganic solution of molecules, and he observed that the light's actually rotating from one plane to other plane. So there is the deviation, the rotation, degree of rotation. So this is basically the observation. That time nobody knows what is the chiral center, what is the stereogenic center, what the structure of the molecule, even it was not very clear, but this observation was there. So this observation actually materialized later on Beethoven concept from Louis Pasteur's study, when he could isolate or crystallize basically sodium and ammonium salt of tartrate, and he could separate both of them physically, and then realize that one of them rotate clockwise, the other rotating the anti-clockwise. So what does it mean? That means it's just not the rotation. There is a sign involved. Okay. So then he thought that probably this tartaric acid rotating in plus minus form. So these are the two different forms, obviously. And indeed, he separate both of them, and they find, okay, these are the two different material. They are rotating in two different direction, and everything is fine. Okay. So you have the buyer to realize that some of the organic molecule can rotate light. Louis Pasteur add more information that not only it's rotate, you can have the same molecules. One is rotating clockwise, other is rotating anti-clockwise. But then again, the problem is, what is the reason? Why some of the organic molecule does this and some are not? So then these two scientists came and with a great thought that whatever the observation is reported by Pasteur, it's probably because of the carbon here. So they call this is an asymmetric carbon. What do you mean by asymmetric?
Many participants reporting that your sound quality is very low, sir. Can you improve it a bit more?
Okay, let me check if I can. So,
Better you can use a headphone.
yeah, actually I'm using a headphone, but somehow okay, just give me a minute. Okay, I'm just leaving the presentation. I will be back in a minute. Just give me a second. Hello, is it better now? Hello?
Hello.
Is it better now?
It is a bit more louder. I think you can go ahead
Is
with
it
that.
better now?
Yes, it's better.
Is great? It's fine now?
Yes, it's fine.
Okay,
Fine.
okay. So I'm really sorry for this kind of disturbance. Let me start my presentation. So can my slide visible? Is my slide visible?
It's visible, sir.
Okay, in the full mode, right? The full presentation mode. Is it in the full presentation mode?
Yes, sir. Yes.
Okay, okay, great. Okay, so if sound is good, let's start. So what I was talking about that, now by this time it is realized that, I mean, it's just a thought came from Van der Leeuwen that this is just because of the asymmetric carbon. At that time, it is also they thought about the carbon with the 4 different hands, and carbon with the 4 different hand got a orientations, and orientation is a tetrahedral orientation. So this is now developed, but still something is not clear. What is not clear? So until now, again, let's say conclude that part, that the Louis Pasteur observed something, that there is a 2 component within a molecule that can rotate light from one is clockwise, one is anti-clockwise. And then these 2 scientists put a tremendous thought on this, that just because of this, this is all happening because of this stereogenic carbon here or asymmetric carbon here. These are all fit with this observation until now, but something remain problematic or confusing. So this is the tartaric acid. Well, so it's a positive rotation. This is another form of tartaric acid, is a negative rotation. There is another form of tartaric acid which Louis Pasteur could not separate into form, and neither this molecule rotate plane polarized light.
The slides are not moving, sir.
Slides are not moving. Oh. Is it moving now?
Moving, sir. It's moving.
Okay. Now is it okay? Slides are moving?
Yes, it's moving.
Okay, great. So I left here that this until now we had this kind of explanation of this observation that there is a 2 form of tartaric acid, and this is all happening because of this flame, this asymmetric carbon over here, and this is well fit with this observation of Louis Pasteur. But something is problem, as I said, this is a mesoform of tartaric acid. Here also you have a asymmetric carbon, whatever you call in the form of carbon with a 4 different hand, but it is not able to rotate any light in the plane polarized light, so it's optically inactive. So how can you explain this? Moreover, there are several other molecules. Look at this molecule. There is a carbon, but not with the 4 different hands. Look at the molecule here, it's the same thing. So there is not even a stereogenic carbon. And similarly, this molecule, some inorganic materials, some organometallic complex like this, these are also chirality. So how can you define what is chirality? It's a remain problem, right? And chirality is just not because of the carbon molecules. Chirality can be found in any heteroatom, any atom with some sort of particular orientation or something that will come in a minute. So there are cases where you have a phosphorus stereogenic center, nitrogen stereogenic center, probably not here, but in this case, and also sulfur or silicon, almost everything you can do it. So then
Sir,
it is.
not moving, sir.
What is the problem?
No, sir. Please select, sir, one by one, sir. I think that will work. Sir.
Is it moving or not?
It is in, sir, origin of chirality. Let's see origin of chirality.
Why it's freezing? Let me start again. I do not understand why this is happening. Can you see the slide? Is it moving?
With heteroatom.
Yeah, this is a chirality with heteroatom. So now with the chirality, the definition.
Yes, yes.
So is it, this is moving now?
Now it's moving.
Sorry?
Now it's moving, sir.
Now it's moving. Okay. So now you can see the full presentation mode?
Yes, yes, yes.
Okay.
Absolutely.
Okay, great. So I'm going back again, the heteroatom. So is it okay now? Can you see the chirality with heteroatom?
Yes.
Okay, so this is the slide number 14. Okay. So as I was talking about, this, that means the chirality is just not because of asymmetric carbon. It could be with any atom. Okay. So then what is the definition? Then the most general definition is come from Lord Kelvin, that I call any geometrical figure or groups of point chiral and says it has chirality if its image in a plane mirror ideally realized cannot be brought to coincide with itself. So that means whatever we call, so now onward, please don't call this is chiral because of the chiral atom. So just find out if you have a mirror image relationship and if the superimposable mirror image are there or not. So this is basically absolutely important in order to say any entity is chiral or not. Fine. So we have definition. We understand why there's a rotator plane polarized light. All these things fine, but how can we present the molecule? How can we present chiral molecules? So it's a slide number 16. Everybody can see it, right? Hello?
Yes.
Okay, great. So then obviously Fischer introduced a very interesting thing. Even today we use this Fischer projection. It's a tremendous contribution in this chirality, the how you can present the molecule, because this is a three-dimensional orientation, three-dimensional phenomena, but we are working on the two-dimension, right? So you all know this thing. So this is a three-dimensional orientation of a stereogenic center, or a molecule having a stereogenic center, or any molecule with sp3 hybridization. And now obviously we press it, we get a two-dimensional. That's why we call this is a Fischer projection. And this is basically the projection, not the real molecules. Fine. So you all know all those things. So what is a chirality, and now we define how you can present it, and now you know the chiral molecules, or there is several of isomerism. But what is important at this stage is here.
Sir, fast ball
If we talk about, so what I'm talking about, that the stereoisomer, because if there is a optical rotation, then we talk about stereoisomer, and the stereoisomer there is a configurational isomer, and if there is a mirror image, then we talk about diastereomers and enantiomers. Now these are the very important, particularly the enantiomer for asymmetric synthesis, catalysis, whatever you call. Okay. Enantiomer is important. Now let me show you why enantiomer is so important. Look at this molecule. So this is a carbon. This is a natural product, right? This is a R form. Only stereogenic center is here. This is R and this is S. So R we can find on the leaf. S we can find on the seed, right? And they have a different order. So just changing the enantiomers, you find the different behavior, different physical property. This is all because our body is made of chiral materials, and this is the one sense of chiral materials. So then if you bring somebody which has this kind of property, so this will bind with a particular center, not the other one, or other one might bind with the other center. So therefore we find it, so our body acts as a detector. Okay, so that's why this is very important, to have only molecule with one sense of chirality. There is another examples. So limonene. So look at this. If it's an R form, then it's a lemon. You find in the lemon. If it's an S form, and if it's an R form, then you find it's an orange flavor. It's the same molecule. Just stereogenic center sense of chirality is different. So these are the enantiomer, but they are in different places. Well, so these are all fine, taste, flavor. So what do we bother about it so much with the enantiomer selectivity and all those enantiomer asymmetric catalysis? Because of these things. Look at this. This is such a painful experience we had. I mean, the world faces. So because of the wrong enantiomers, okay? So these are all happened because this kind of thalidomide was a drug. It's long back, and it was used for to make feel better of the women who are expecting babies for morning sickness. And it was found out that when it is used as in the form of racemate. Racemate means it's a mixture of 50-50 mixture of both the enantiomers. And later on, it is found out that our enantiomer is actually the drug action and shows drug action. The other one is not. It is basically poisonous. And that lead to basically birth defect of babies. And this is such an important things. So if you are dealing with a drug which has a stereogenic center, you have to be very, very careful. You have to provide all the pharmacological data that the other which enantiomer is active and which one is not active. And then nowadays rule is the general guidelines, they strongly encourage the development of single enantiomers, not the racemate or not the mixture. And if you are using mixture, you have to provide all possible data that other enantiomer is not toxic. Okay, so this is absolutely important. That's why asymmetric catalysis nowadays is extremely important, because I'll come in a minute that this is probably only the best way to make stereogenic center in large excess compared to other enantiomer in good yields. Okay, more examples. We all use this molecule. What is it? It's ibuprofen. There is a stereogenic center. So S-ibuprofen is active in enantiomers. Look at this. So the S1 is active, and it's actually in 15 minutes, 3 times faster. Reduce the side effect of 50%. So what does it mean? So you check your prescription. If doctor give you ibuprofen, and if it's a 600 milligram, so that means if it's a racemic, then basically 300 milligram is active drug, rest 300 is not. So if you use only one sense of chirality or enantiomer-enriched ibuprofen, then doctor will provide only 300 milligram dose, not 600 milligram, because 50% anyway is not an active molecules. So therefore, the rest of the 50%, body has to find a way to get rid of from our system, because it's not an active drug. So that is the problem. That's why it is important to make this molecule in enriched form, only one form in large excess, so that we can use the enantiomer-enriched drug. Even nowadays, I mean, before this lecture, we are getting the information that what is actually going on. You all know the pandemic situation, and there is a controversy that whether it's a hydroxychloroquine is useful or not. But I'll just focus on the concept of chirality, or the perspective of chirality, that there is a recent study. It says the hydroxychloroquine, there is a true form of enantiomers, right? Because there is a stereogenic center. And the very preliminary data says that indeed the S form is found to be 60% more active against the COVID-19 than the R form. But again, this is just a preliminary report, okay? But what I'm trying to say, whenever you're using a drug molecule with a stereogenic center, then we should be very, very careful that one enantiomer could be active, other could be dangerous. If it is not active, then still okay. But if it is poisonous, if it's bind somewhere else, then we'll have a story of thalidomide things which we don't want to repeat it. Again, this is a very important drug. I mean, nowadays doctors even prescribe this dexamethasone, and even WHO says this is important. And indeed, I talk with two of my doctor friends, and they are basically using this as a steroid drug. And here, the drug activity is depend on this methyl. So if its methyl is down, then this is important. If it's up, it's a beta form, then it's not active. So this is absolutely important. And why this is important? Because of that. As I said, our body is made of chiral materials. So it's just like a receptor, like in this form. Now this one, this is a drug entity or anything, it's coming to our body, it will properly fit the way, the place where we want to fit it. So it's perfectly fit with the receptor, but not this one. So these are the enantiomers. So look at this. This is just the opposite. Therefore, these are the enantiomer. This is not going to fit here, but this one is going to fit here. Now, if this bind with somewhere else, then it will do different activities, which we don't want. So that's why this is very important. And then what is then asymmetric synthesis? So we have to prepare this molecule in the one sense of chirality. So this is the asymmetric synthesis and how we can do it. Asymmetric synthesis is a reaction where an achiral entity is converted by a reactant into a chiral entity such that the stereoisomeric product are found in unequal amount. So for a moment it's just a chiral entity. It could be chiral entity. I will discuss those things. But the normal definition for the graduate student is just like that, that if we transfer from a chiral entity to chiral entity and if we produce them to enantiomer and not in 50-50 mixture, then in definition we can call this is an asymmetric synthesis. How we can do it? What is the theory behind it? So look at this. So I think most of you know this reaction. This is a very simple reaction. Just consider any prochiral ketone, add organolithium reagent or linear reagent, whatever it is. It's just a demonstration of a model reaction. Now, if you have this kind of ketone, obviously, then you add something nucleophile, then you have a stereogenic center forming, just like this. So this is a ketone, you add butyl lithium, you get this stereogenic center. Molecule contain only one stereogenic center, so we can expect two enantiomers, and reaction is going through this kind of transition state, and this transition state are equal in energy. So this is basically enantiomeric transition state, and that will lead to enantiomers. And since enantiomers are equal in energy, therefore we just cannot control. If we add this butyl lithium or any lithium with this kind of reagent, this kind of substrate, we generate a stereogenic center. We generate a molecule with a chiral center, but it doesn't mean we have an asymmetric synthesis. No, because this is a racemic synthesis, because both enantiomer are in 50-50 form. So how can you do it? So obviously you all know we have to go through definitely a diastereomeric differentiation process. So what does it mean? That means the transition state should be diastereomeric transition state. So now look at this molecule here. So this is a ketone with a stereogenic center like this, and this is fixed. And what is important? This is the one sense of chirality. Look at this. This is not racemic. If it's a racemic, then scenario will be even more complicated. So this is one sense of chirality. Now you have a sp2 hybridized center with the ketone. You add it butyl lithium, then you generate another stereogenic center. Now if I follow the curve, so here was my starting material with the stereogenic center. Now moment it's go the transition state, then you have a another stereogenic center. So there is a scenario for diastereomers. And we know diastereomers are different in energy. They are different molecules rather. So obviously the transition state will have a different energy. And then which one will have lower in energy, that will produce in large excess. So there we can see the induction. There we can see the difference in the ratio of the two enantiomers. Okay. So for any asymmetric synthesis, this is important, very important, that somehow you have to come across the diastereomeric transition state, and the step is called diastereomeric differentiation step. So this we can provide through a substrate chirality, because this is a substrate chirality, or with a catalyst. So by any means, if we can come across this kind of scenario, then we can have an asymmetric induction. Okay. So now you know what is racemate. What racemate means 50-50 mixture. Racemization means when one enantiomer is transferred to the 50-50 mixture, then is a racemization. But and we know that what is enantiomer differentiation, what is diastole differentiation, and by now we know that through only diastole differentiation's transition state we can have an induction. But this is all fine, but how do we know? How can we measure if there is any induction? So obviously nowadays we use HPLC. End of my talk I will show you that. But the traditional one, obviously the polarimeter. So you measure the optical rotation. So if it's a 50-50 mixture, that means the racemate, then as you can see, they cancel out each other. So 50% plus, 50% minus. So then you come across a zero rotation. So that's why just using the polarimeter, just using the optical rotation measurement, you can't tell if molecule is chiral or achiral. Because if molecule is racemic, that will be zero rotation. If molecule is achiral, that would be zero rotation. So please, for the students, don't, whenever you think about how we can determine the chirality or how you can observe the chirality, don't think it's a polarimeter. Polarimeter is good when you have a excess. If you do not have excess, you don't see anything. So never use the term polarimeter for checking the chirality. Okay, but if you have excess, then it's good. Look at this. So it's a 90% one enantiomer, the red enantiomer, 10% is the green enantiomer. So the 10% will be cancelled out. Then what would be the excess? 80%. So this is we call enantiomeric excess. We write it EE. So enantiomeric excess. Okay. So this is very simple way to calculate the percentage of enantiomeric excess. This one, I am sure you all know these things. Okay. So now we know what is the importance of enantiomer material. Why do we need to prepare it? Now we know the theory how we can do it. But then let me show you what are the technique we use nowadays. So obviously one of them is the resolution. You can argue that, okay, why you need to synthesize? You just resolve. Because we take a racemic material, A form, B form, you resolve it, you learn these things. You put acid, you throw base, and then you make a salt and then separate it. But if you do this, then what is the problem? Of course, you can get an enantiomer material. But the problem, look at this. This is the racemic mixture. Now this is your chiral stationary phase. So in a sense, let's say, if it's an acid, then it's a base. And then it has to bind there. And after binding, which one is the properly matched, like this one. So all bind properly, then it will come later. And the mismatch, then it will come early. So this is the concept of chiral HPLC separation. Okay. But if you want to do synthesis through resolution, then you have to use this platform stoichiometric amount. So, but it has to be again one sense of chirality. So from where are you going to find it? So this is another problem. So the modern way to synthesize the enantiomer-enriched molecules or complete the enantioselective synthesis is we can start from chiral pool synthesis through chiral pool using chiral pools like the nature produce this material like sugar, tartaric acid, sugar, or even amino acid. Then you get a long way synthesis to get your target molecules. And this is quite useful. Just I want to give you a flavor of that how people do it. So look at these molecules. The babidoxine is extremely complicated molecules with a tremendous amount of stereogenic center, but we can do it with a simple sugar molecules, which is a chiral pool entity, and it's a 40-step synthesis to get the target molecules. The other approach, so you take chiral pool molecules and do some transformation and make a new molecules and use that one as an auxiliary. So this is a chiral auxiliary which is coming from chiral pool entity, but with some simple transformation. And this is not a linear synthesis. So once I have this material, I can combine this with a substrate, which is achiral. Now, after combining this, now see the chiral information is attached to this achiral substrate. Now, if we do the reaction and we generate this achiral substrate to chiral product, if you remember the curve, then you have a diastereomeric scenario because there is a one stereogenic chiral information and one is going to form. So there is a diastereomeric scenario. And then obviously one will form in large excess, other will be less, depend on the obviously transition state energy. And then later on it cleave. So this is absolutely fine. But again, the question is, why do we need catalysis? This is absolutely fine. So look at the step. You have to have this material Then number 1, you have to attach them. Then number 2, you find the way to separate them. And number 3, you have to remove it. Like this. This is a real example. So look at this. This is an amino acid form, aminol. And this is your substrate. You make this oxazolidine ring, and then you combine it with acid chloride. Then put base, then you have enolate. Then you put an electrophile, then you generate a stereogenic center. Now this is down, so the electrophile will come from the top. So this is the Evans alkylation method. This is absolutely useful. Even company use it today. But still the problem is making this molecule, attaching this with the substrate, and then again you have to clip this in order to remove the substrate from the auxiliary. Another approach, you can use a chiral reagent. So reagent itself chiral. So if reagent is chiral, then it will deliver the you perform the reaction in a controlled manner, like this, and then obviously the reagent is dead, so that you destroy the chiral information, chiral reagent, but you have to use the chiral reagent in large excess, at least stoichiometric amount, in order to get a good yield. So that is the problem. Look at this. So this is a chiral boron reagent, and then if you want to reduce this carbon, so this is basically the borohydride type of chemistry. And then you do this hydride transfer, and then finally you make this molecule. So this is fine, but this is an expensive material, right? And end of the day, you don't find it. So you lose the chirality, all the information. So that is expensive. So what is the best way? So best way is the chiral catalysis. So through catalysis, you get the asymmetric induction. So what does it mean? So does it mean you take a little bit of chiral catalyst, or the catalyst with a 1 sense of chirality, and now this is not a permanent bond formation. This is the incipient bond formation in the form of any kind of interaction. It could be covalent, it could be non-covalent, but it will bind with the substrate during the reaction and then deliver the product, and after the product it will remain in the same form. So this is the best way to do asymmetric synthesis, through asymmetric catalysis. And there are many concepts of asymmetric catalysis. I just summarized some of them here, like a metal-based catalysis. For example, here you use metal as the active center, and then you bring a ligand, and the ligand got the chiral information, and then you can do the induction. And this is a biocatalysis where enzyme act as a catalyst. And today I'm mostly focusing on the organocatalysis. Organocatalysis means the chiral organic molecules are used as a catalyst. So this is the small molecules. For example, let's say amino acid, any sugar. Without transforming this to anything else, if we use just that one for catalysis, that would be interesting. Or you transform this amino acid to a small molecules, and then that molecule can do catalysis. So what is the advantage? The advantage is the diverse range of activity, you can find it. And this is a low cost material because nature produce all of them, and we're using that one directly. There is no metal ion, there is no expensive ligand. It's a moisture and air stability. So most of the reactions are not in harsh condition. Okay, so because this kind of reactivity we observe in the nature, so it's basically mimicking from nature, no metal impurity and catalyst recovery, and you can recover also this catalyst and reuse it. So these are the very important points nowadays for catalysis, particularly for asymmetric catalysis. But what is the limitation? Catalyst loading is very high. Obviously, since this is not a moisture sensitive or air stable, so there is a less reactive. So there is a little bit of sluggishness on the reactivity, therefore we need to use a little more in excess. And since this is as I said, we are mimicking from nature, that means there is this kind of reactivity there, and therefore there's a possibility for a background reaction. What is the background reaction? Imagine we are doing asymmetric catalysis, and if we remember my catalytic cycle, all the product that is forming through this catalytic cycle, they only give an enantiomer induction. But product can form in some other way as well. If that happen, then that will give a racemic product because catalysis is not involved there, right? So that is we call background catalysis or background reaction, not catalysis, background reaction. So if background reaction is happening, then you're going to lose your enantiomer selectivity, right? So let me give you, I mean, you don't have to look into, or I mean, don't have to understand all those things, but just a flavor you can get it. So which kind of molecule we are used as a organocatalyst? So these are the purely organic materials. There could be a organic part like metal ion, but metal ion would not be an active catalyst, active part in the catalysis. So what is the most popular one? The amine catalysis. There's like a proline or derivative of prolines. Also the carbene catalysis. So look at this. This is the N-heterocyclic carbene because you have a heterocycle. And this in this form or in this form. There are many others. Just a representative example here. So this we will give through the covalent interaction. And this is mostly known for the non-covalent interaction like acid, bone-state acid. You all learned the acid catalyzed aldol reaction, acid catalyzed esterification reaction, acid catalyzed acetylization reaction. So these are all basically hydrogen bonding catalysis or ion pairing catalysis. And these are the reaction can be catalyzed with acetic acid. So acetic acid is an organocatalyst. Similarly, this is the phosphoric acid with this kind of axial chirality, and this is the basically thiourea or urea derivative where you have a hydrogen bonding donor. And also you can use this kind of salt, so quinine or this kind of salt. So this act as a ion pair catalysis. Okay, so these are the kind of three. There are many examples of this one. Just if we want to categorize, we find these are the three major category for asymmetric catalysis using organocatalysis, in the form of organocatalysis. In our group, we are focusing mostly on N-heterocyclic carbene chemistry. So I'll give you quickly just a flavor that what we are actually doing in our group in few slides. And let me tell you why we are working on N-heterocyclic carbene. So this is the carbene, you know, the carbon with a bivalent structure. So this is the carbene. And this is a strong sigma donor. It has a good bone state basicity and moderate pi acidity. That means because of this, this is the very versatile and very easy to prepare. How you can prepare? You take corresponding azoleum salt, the quaternary ammonium salt, and then you put a base and deprotonate this CH, then you get a carbene. And this carbene is quite stable. Why this is stable? Because if the nitrogen lone pair is there, so it can donate to empty orbital. And at the same time, there is a possibility that there is a back donation. Because of this push-pull system or synergistic effect, this is quite stable. So for any kind of catalysis, what is important? The catalyst should be reactive. At the same time, there should be some degree of stability. Otherwise, it will destroy in the reaction, right? So carbene kind of hold all these properties, and therefore we are very much interested on carbene. Many people are working in our group also. We are working. So we are working in the using mostly these two properties. There's a sigma donor property. So sigma donor property means it's donate electron and make a sigma bond. So that means it's a Lewis base. Now I will represent NHC in heterocyclic carbene like this. This is of course the stereogenic center is there. Now if this is the Lewis base, just like amine, if there is a reaction with aldehyde or the electrophile, they will react just like a nucleophilic addition. And then after that, what would happen? You can get this kind of formation, right? So there will be anion, then there is a hydrogen shift, and then you have a hydride. Proton shift, then you have an anion here in this. So what is it? Look at this. There was a carbonyl. So this carbon was del plus, and now this carbon is del minus. Isn't it a umpulum? So we do umpulum in the through of catalysis. You learn with the thioacetal formation or ketal formation, and then you put deprotonation. But it's just with the catalysis. See, there is no harsh reaction. Now, this is extremely electron rich. Obviously, with this intermediate, you can do plenty of reaction. If you throw any electrophile, that's going to react. But today, I'm going to focus some more, even more different step. So this is extremely electron rich, right? Look at this. This is the nitrogen with a lone pair. There's a double bond. There's a OH. So this double bond is extremely electron rich. So if you provide oxidant, then this will oxidize. And if it is oxidized, then what will come? We come a acyl group attached to a azolium group. Isn't it like a acyl chloride equivalent? So we are basically aldehyde to acyl chloride. Otherwise, how do we form acyl chloride? From aldehyde to carboxylic acid, then thionyl chloride, then you get a acyl chloride. But here, look at this. Just simple catalysis within the reaction and with the oxidation, you get this one. Now, you bring a nucleophile. So this nucleophile going to react, and then acyl group will transfer to nucleophile. And then catalyst will be free, just like this. So nucleophile react, then anion come back and release the catalyst, and which will be carbene again. This will be ready for the next step of the reaction. This is exactly what we talk about the catalysis. See, within the reaction, catalysts remain unchanged. And then by this way, you transfer acyl group to a nucleophile. Now, if this catalyst is chiral, we can do all this reaction in the chiral environment. We can all generate diastereomeric transition state. We can all expect to have an induction. So using this concept, recently in our group, we have developed a kinetic resolution of method for primary alcohol. So let me take a few minutes to explain what is kinetic resolution. If you remember, at the beginning of my lecture, I said there's a possibility you can resolve it. Fine, but that's the traditional resolution. But this is the catalytic kinetic resolution. Okay, what does it mean? So this is my substrate. S stand for substrate, and R and S is the sense of chirality. So that means this is a racemic compound, racemic, right? So if you remember at the beginning, I said few minutes ago, I said that asymmetric synthesis where we have a achiral substrate transfer to chiral material. Is everything is okay?
So which one is poisonous?
Hello? Am I audible to all of you?
Audible, sir. Yeah,
Okay.
audible.
Okay, okay, great. So if you remember, I just said that for asymmetric induction means achiral molecule you transfer to chiral molecule. But I told you this is for a moment. But now, see, I am working with the chiral molecules, but racemic. So this is, we are going to do resolution through catalysis. So this is S form means the substrate, which is the R enantiomer and S enantiomer. Now we are doing a reaction in a non-racemic transformation. We call this is a non-racemic transformation. What does it mean? The transformation will not give a racemic product, right? So this is the asymmetric catalysis, isn't it? So if we do this, so this is, let's say this is from R to give a product to R, S enantiomer give a product S. Now this is the rate of a reaction. So this is the rate of a reaction of the other enantiomer. Now if this rate are different like this, so this is much faster than this one, then what happened? This all S will transfer to product. Then what will remain? All R sense of chirality will transfer to product. Then what will remain on the left hand side when reaction is not taking place? That's a S form. So we are resolving, right? So S form is the unreacted substrate and R form will transfer to the product because the R enantiomer reacting in much faster rate under this condition. So this is basically the resolution with the rate, therefore we call this is a kinetic resolution, and it's very much like that. So this is the racemate. And now this one is a minor product. Let's say this is for S form and this is the R form. And if R form having a lower in energy in the transition state, because of this energy difference, all R will transfer to the product and left over here the S unreacted starting material. And if we can stop the reaction at what stage? It's 50%, right? We don't want to push the reaction. We want to stop the reaction when there is a 50% conversion. 50% of the starting material transfer to the product. Then what will happen? All our sense of chirality will transfer to the product and the substrate, that will be the S form. So recently we have done that and using this NHC catalyzed acyl transfer chemistry. So I'll just give you an overview that what was known. So it was known that you can do this kinetic resolution, but the substrate they use this kind of, this is a secondary alcohol, all of them, you know, this is a tertiary alcohol. This is again secondary alcohol. This is a special kind of secondary alcohol, and this is also a secondary alcohol. Okay. Now, what is important here? So all are secondary alcohol, and another important thing is most of the cases this alcohol actually the reactive center that connect directly to the stereogenic center, and if that happens, then it's very easy to control the induction because it's very close to the stereogenic center. If it's very away, then it's very difficult to control the conformation. That's why resolution of this one, look at this, this is the primary alcohol. So there is one carbon apart from the stereogenic center. It's extremely difficult to resolve. And moreover, this is highly reactive. And if it is very reactive, then you can have, if you remember, as I said, there is a background reaction, there's a possibility of background reaction, and there is a conformational flexibility. It's conformationally very flexible because it can rotate easily, right? So in order to resolve this one, we thought it would be first, what we have to do, we have to basically control the conformation. How we can do it? If X is the amide with the NH, then there is a possibility you can go for open chain and the cyclic form through hydrogen bonding between OH and NH. And if that happens, we all know the cyclohexane has a restricted rotation, right? So the chair form and inversion of between these two chair form, there is some sort of energy involved. So if we can do that, then obviously we can reduce the conformational flexibility and we can reduce some sort of restriction. And this is exactly we thought about it. And then we thought if we have this kind of geometry and then we bring our catalyst and use that reaction, then we transfer acyl group to alcohol and stop the reaction at 50%, then 50% will be ester, 50% will remain as alcohol, and then we can separate it. So that was the thought. And I'm not going into details on the reaction, you don't have to do it. Only thing is just focus here that we use a base because I told you base is required to deprotonate this azoleum salt to generate carbene. So obviously initially we use small amount of base because we are using small amount of this one. So if we do this, then we get a ester, this is the ester, with a good enantiomeric ratio. So this is the ratio. This is not excess, this is the ratio. So one is 96, one is 4. That means the excess is 96 minus 4, 92. Okay. So this is we are getting directly from the machine. So this is a ratio. But the ratio of alcohol is very poor, extremely poor. Just think about that. Why? Why ester we have excellent enantioselectivity, but not the alcohol. Then what we did, we put 200 more% of DABCO, so we increase a lot of DABCO. It's just a 2 equivalent. 200 more% means 2 equivalent with respect to the substrate. And then we find, look at this, excellent enantioselectivity for the ester and excellent enantioselectivity for the unreacted alcohol. So if the enantioselectivity is greater than or equal to 90%, then we consider this is the useful method, otherwise not. So in this case, this is a 92% enantiomeric excess for ester, and this is a 90% enantiomeric excess for the remaining alcohol. So this is absolutely fine, right? So and then this is not important for you. This is just whenever you develop a method, you have to test this method with a different substrate, and these are some representative substrate, as you can see. And look at this one. This is such a simple molecule, right? It's a methyl group and OH, and there is no other things, but still we can control with excellent induction for this kinetic resolution. Now, this is very important that I said that our hypothesis, there was a hydrogen bond formation between NH and OH. What is the proof for that? Everything you have to prove it. Otherwise, it is difficult to believe, right? And this is what I like to draw attention from the graduate student, that you probably do not know the other analytic technique, but these are extremely powerful, where you can really figure out what is happening inside the reaction mixture. So here we did a NMR study, nuclear magnetic resonance, and these are the 1H NMR, proton NMR. I think you have a little bit of idea on this. So this is the cyclic form, and this is the acyclic form. So we are measuring the NMR at 298 Kelvin. So that means the room temperature, 25 degrees. So simple NMR, and this is the peak for NH, this NH, this is the peak for OH. And we are interested in this two peak because these are in action. Now we cool it down to minus 30 degrees, 243 K. We found there is a huge downfill shift, is 8.738 to 8.997 for NH. and similarly for OH. So that means something is happening. And downfield shift means you are reducing electron density from there. And this is only possible if this kind of interaction is there, right? There is a hydrogen bonding, so there is a downfield shift between both the cases. Now, if we few minutes ago I said if we use excess DABCO, the 200 mole% DABCO, then we get a good enantiomer selectivity. Okay. Then why it is like that? So that means DABCO has something to do with this kind of geometry, right? So how to prove it? So again, we did 1H NMR study. So look at this. This is the room temperature, 298 Kelvin with a 200 mole% DABCO. Now, if we look this proton NMR and the proton NMR below, which is blue in color, and if we see the NaOH signal, we find 8.738 ppm. Here is 8.895 ppm. That means even at room temperature, DABCO actually participating to stabilize this kind of hydrogen bonding interaction. And because of that, OH signal is vanished. It's not there because it's exchanging. Because DABCO is interacting with OH, make it more acidic through hydrogen bonding, and that allowed to get a hydrogen bonding even at room temperature. Now, if we cool it down to -30, then it's an enormous downfield shift. So originally it was 8.738, now it's a 9.261. So this is a very much proof that indeed we have this kind of hydrogen bonding interaction, which is again stabilized by base DABCO. And based on that, we propose the transition state for this reaction. So these are the two enantiomers. When one you have H axial, when you have H equatorial of the substrate, because substrate is chiral. And now it is interacting with the catalyst with a, here is the acyl moiety, and then there is a DABCO hydrogen bonding with OH. Under this scenario, as you can see, this is probably the best possible scenario where you can have a minimum steric interaction, right? So this is the fast reacting enantiomer, so it will give a ester formation, and this is the slow reacting enantiomer that will remain as it is like alcohol, because this R is in axial position, which is in interaction with this amide aniline moiety as well as the R group of the acyl compound. So this is a very slow reacting enantiomer. So through this, we developed a kinetic resolution, and I'll just give you one more example where we use NH in different form. So I told you NH is good for covalent catalysis, but again, it's a very simple observation that led us to do this kind of chemistry. I said several times that azoleum salt, you deprotonate, you get a chiral NaC, right? You get a carbene. So this is acid, this is base. So what it is? It's a conjugate base, right? So if it's a base, then if I provide another acid, then this will deprotonate, then you get again the ion. There was an ion. This is also ion pair. Now, if this is my substrate, so that means the organic compound with the acidic hydrogen, then by doing this, we can basically activate the substrate, and now this activated substrate will do the reaction in the chiral environment, right? So then we can expect the asymmetric induction. So this is a very simple observation through the anion metathesis, because this anion is X, now it's a nucleophile or other form, NU, nucleophile, yeah. So these things was not known when we started actually. And then we thought about, so what would be important? In order to do that, see, everything is in equilibrium. So you have to maintain equilibrium toward the forward direction in order to get a desired transformation in the good induction. So how can you do it? So for that, the guideline is the pK. So this azoleum salt, the pK is in this range. And then this amide, beta keto amide, is pK in this range because of this NH. Now, that means this carbene can deprotonate, and it can deprotonate, then you get a chiral ion pair. Now, once you have this chiral ion pair, we can do conjugate addition, and that's what we did. We took this kind of Michael acceptor for 1,6 conjugate addition reaction, and we get an excellent enantiomer selectivity. There is no covalent interaction with NHC. So this is purely non-covalent interaction throwing through the ion pair mechanism. And last year also we complete this reaction where you have Again, this is the chiral material. Look at this. These are the achiral. These are the achiral. We are generating the stereogenic center. Here, this is the chiral entity. But after deprotonation, it forms a chiral intermediate, just like this, So lose the chirality, and then again it forms the chiral stereogenic center in presence of a chiral catalyst. So there is a diastereomeric transition state, and we get excellent yield as well as enhancer selectivity. And this is also, we prove that through 1H NMR study that indeed we are forming the chiral ion pair. So this is the azoleum salt. We take NMR, and I'll just draw your attention with this peak. This is basically the CH peak here. And now you put a base, then you deprotonate. So if you deprotonate, that should not be there. So this carbon is vanished. See, this is not here. Then if indeed my hypothesis is correct that there is an ion pair formation on and this act as a base, then this H should be there, like this, right? And indeed, it's reappeared. And reappeared in slightly in upfield because of the anion is different. So this is very much proof that indeed it's going through like an ion pair mechanism. So, but again, we need some more data to confirm this is the ion pair mechanism or hydrogen bonding mechanism. So we propose both the transition state, that it has a interaction and then it transfer to this nucleophile transfer to electrophile, and everything is happening in the chiral environment and through a diastereomeric transition state. So we expect good enhancer selectivity. So this is basically the probable transition state, as you can see. So there is a hydrogen bonding interaction or ion pairing interaction involved with the catalyst and the nucleophile. And there is my electrophile coming, and we have a rephase approach of the nucleophile, and then we confirm this absolute stereochemistry through X-ray analysis. Okay, so I hope I able to give you that what is basically asymmetric catalysis, particularly with the organic molecule, and what is the asymmetric organocatalysis. And I told you during my lecture that the traditional approach to measure the induction or measure the enantiomeric excess was the optical rotation, but nowadays we don't use it. Nowadays we use chiral HPLC or HPLC on a chiral stationary phase, that's a CSP. And this is just to give you a flavor how this HPLC should look like. Look at these molecules. So how many stereogenic centers are there? 2 stereogenic centers here, and another one is here, right? So if 2 stereogenic center, that means we can have 4 peaks, right? Isn't it? So one pair of enantiomers, one pair of diastereomers, and they will have 4 different stereoisomers. And these are the 4 different enantiomers, as you can see. Okay, so this is a racemic compound. That's why they are all 1-to-1. And even in the racemic compound, there is no diastereoselectivity, right? So since there is no diastereoselectivity, all are very much 1-to-1, all 4 peak. Now it's the same compound, but enantio and H. I mean, we are preparing this one through chiral catalysis. This is we prepare with a normal base catalysis, base reaction, where there is no chiral information. There we prepare with using NHC catalysis, and as you can see, only 1 peak in large excess. The rest are very, very small. What does it mean? That means it has a good diastereoselectivity. Also, it has an excellent enhancer selectivity for major diastereomer. Okay, so I hope I am able to give you the flavor that what is chirality and how do we call molecule is chiral or not, and how we can develop asymmetric catalysis. And now let's come back to the original question that whether all these molecules are chiral or not. Now, if I ask anything that whether this molecule is chiral or not, that's not a right question to ask actually, because chiralities depend on the condition. Something can show chirality at room temperature, something can show chirality even at -90, not at room temperature. So it's very simple. Like if I ask any students, any parents about kids that okay, how is your child? The parent will say, oh, he is very nice, obedient, and all those things. Fine, but moment this person, this child put in the hostel, and then I can see different reactivity, and then I cannot compare, right? What parent says and what I'm looking at, because the condition is different. So parents observe child at home where there is a discipline and the child has to maintain the discipline. The hostel, they're free. There's a lot of entropy, right? So that means depend on the condition, you can define something showing the chirality or having a chirality, other are not. So therefore, when you define something, this molecule is chiral, you have to mention the condition. Look at this. So these two molecules, all of them, in my opinion, they are chiral because there is, in this form, there is no mirror image relationship. Okay, no superimposable mirror image. But then the problem is you just cannot hold them in this form at room temperature, right? So something we show the chirality, we call this is the chirality at ambient condition. Some of are not. Okay, so I hope you understand what is the chirality, and chirality is always related to a condition. And I give you a flavor that what we are doing. So finally, I like to thank my teammate. So these are the people basically working in the group. They're the hardworking people, and I think these are very much like the student like you were before, and they come to us, our laboratory, and they developed all this kind of chemistry. So I really thank to them, and I must thank the Google search engine because I get lots of information from the Google. I took some of the slides directly from the Google. I will thank from that. And I must thank also the funding agency, my institute, that's ICS, ACRB, this is the main funding agency because we need money to do research, and CSIR, of course, for funding to support the students. And thank you very much for your kind attention. I'll be happy to clarify any doubts, any questions you might have. Thank you very much.
Thank you, Professor Guin. Now, this session is now open for question and discussion. I would like to request our student to put their question either on chat box, or they can even directly ask Professor Guin. And I must say that language may not be a barrier. You can even ask in Bengali also.
That's right. So I could see one question in the chat box. That's a Monish Das. So there is a question that chiral auxiliary is the catalyst of asymmetric synthesis. No, it's not a catalyst because it's an auxiliary. That means you need that as a stoichiometric amount, because if you remember the model, that chiral auxiliary basically you have to combine attached with a substrate, and then you do the reaction. So if you want to have a good yield, then obviously you need at least one equivalent or 1 mole of auxiliary with respect to the substrate. So then it's not a catalyst. Okay. And in asymmetric synthesis reaction, kinetic control product, thermodynamic control product concept is applicable or not? Okay. Everything is applicable, but you need to know how to do it and where it is, because if there is equilibrium, then you can come across these things. Okay, but if there is no equilibrium, then there is no question of thermodynamically controlled product. Then that will be a kinetically controlled product, right? But if you maintain the equilibrium, there are cases where we can have a good enantiomer selectivity at higher temperature. Usually we do asymmetric catalysis or induction at lower temperature. Why lower temperature? Because lower temperature you freeze the molecule from the vibration, and therefore you are expecting to have a energy difference of the transition state, bigger energy difference. If the energy difference is bigger, then obviously you can have a good induction, because the lower transition state energy reaction will follow the lower transition state pathway than the higher one. But there are cases where the reaction actually follow this kind of concept. Then you have to heat it up. If you heat, then it will come in equilibrium, and after equilibrium it will deliver a product. Okay, you are absolutely right. It is all applicable there. Any other question? Okay, why achiral molecule cannot rotate plane polarized light? So the molecule is achiral, so that means it is symmetrical. If it's a symmetrical, so it's basically every part is same, identical, because it's any light is an electromagnetic wave. So if we have an electron density in a particular direction, then only that will react with the light and then it will rotate. Now achiral molecules is a symmetrical molecule, right? So every direction you find the same kind of electron density, which is not for a chiral molecule. So that means the molecule who will have basically the different orientation. And if the different orientation, that means there is a different in a electron distribution, electron cloud distribution, I should say. Okay, and that's why this is very important things. That's why there are molecules which is even in inertia enriched form rotate very little optical rotation. So for example, if the molecule is made of entirely hydrocarbon, like let's say ethyl, methyl, isopropyl and butyl, this stereogenic center containing molecule is extremely poor in the rotating plane polarized light because it's not reacting with the light. That's why.
Sir, in optical rotation,
Mm-hmm.
what kind of interaction is going on between molecule and the component of electromagnetic radiation?
So is actually the
Is the electrical component of the electromagnetic radiation interacting with the electronic environment of the molecule or something else?
I mean, obviously this is a more like a physics oriented things, but what I believe this is very much like a electron environment interaction, right? So it's an electromagnetic wave. If you provide electron density, it will rotate. It will move away, right? So the molecule, if there is a one direction of electron density, then according to that, it will interact with the light and rotate the light. Okay. Asymmetric chirality means, what is your question? I couldn't follow it. Tushar, what is your question? Asymmetric chirality means there is no asymmetric chirality.
Something like that.
I mean, if there is no symmetry, I mean, if you break the symmetry, you bring the basically the chirality. Okay. So you can, Vishnupodo, you ask that can we say chiral catalyst or chiral reagent? No, I mean reagent you need you perform the reaction in the lab. I mean if you do the project or like in the practical, see you are using a reagent. Reagent, how much you use? Use 1-to-1 mixture at least, right? So if you want to make ester, you use 1 alcohol, 1 acid, and that has to be 1-to-1, right? With the mole, with respect to mole percent. And then you add a little bit of acid if it's an acid catalyzed esterification. So that means the reagent is not a catalyst. Reagent is a reagent. Okay. Catalyst you need a little bit amount. Okay, 1 mole percent, 2 mole percent, 10 mole percent, something like that, but not 1 equivalent. If you use 1 equivalent or 1 mole percent, then it's a reagent. This is not a catalyst. Okay, Onupam, you ask, sir, which one is poisonous, R or S? No, nobody can say that. Nobody can say that unless you study and really find out that one. Okay, for thalidomide, if I remember probably, I don't know which one, one of them is, but whether R is poisonous or S is poisonous, for example, this ibuprofen S is more active compared to R, because we study this and we know. Unless you study it and we do not, nobody can tell that. Okay, you have to study. Both the enantiomer you have to separate and you have to put it in the body, and then you study the all the pharmacological data and observe the patient, and from there you realize, okay, one is active, one is not. Okay.
Sir, in your recent paper, I have one question.
Yeah.
In your recent paper,
Okay,
did you measure the catalyst loading and turnover number?
Well, I mean, catalyst loading is around 15 more %, and we can reduce catalyst loading, but in that case, what happened? Reaction efficiency goes down. Okay, so it takes longer time. Sometimes we do not see the good conversion. And now, if I see the turnover, let's say catalyst basically that it is a 50% reaction, right? So if I use 15 more % catalyst loading and where my yield is around 45 or 49, then it's obviously 3 turnover only, right? Because we have to stop the reaction by 50%, because we want only one enantiomer should participate in the reaction, not the other one. Okay, so if I go for 100%, then what happen? It will take both the enantiomer to the product, then product will be racemic. Okay, so in that case, turnover is not that important. What is important? It is the selectivity factor. I mean how much selection is happening. Okay, and that in that case is very good. Okay, Vishnupada, you asked me the chiral auxiliary is used as a stoichiometric proportion or catalytic amount. Chiral auxiliary, you have to use the stoichiometric proportion. You have to attach chiral auxiliary with your substrate where you want to do reaction. Okay, so that's why this is auxiliary. It's helping. It's not a catalyst. How to improve the yield of asymmetric synthesis? Is it possible to carry out asymmetric synthesis in simple lab? Of course. I mean, you can perform the asymmetric catalysis. If you have my catalyst, you can perform in your lab also. There is no problem. See, we are doing reaction as -30. You cool it down. If -30 you cannot reach, you just go with the ice bath. Then you get a little bit of lower E, but reaction will happen. If you have catalyst, you can do it. You just take proline. I don't know whether it is possible or not. You can just take simple proline and you can do aldol reaction in your lab. And then you isolate the product and measure the optical rotation, because I think polarimeter is there in your lab, in your college or somewhere. So you can clearly measure that and clearly see there is a perfect induction. Absolutely, no problem. Thank you. Any other queries from anybody?
Sir, I have one trivial question.
Yeah, sure.
Sir, in measuring of the enantiomeric excess, sometimes we measure or we calculate in terms of concentration of the both the enantiomer, and sometimes we can also calculate by using the optical rotation. Between these two quantity, which one is more appropriate?
See, I mean, what we do, we prefer that we keep the concentration one. Okay. So irrespective of molecularity, if you have just 20 milligram of compound with a 200 decimal system, then obviously you have concentration 1. And now you measure the optical rotation. Okay. But if you are talking about the measurement of enantiomeric excess, then none of these are not correct. What you have to do, you must have enantiomer pure compound, reference compound. So, and you make particular concentration solution with a particular solvent, and then you measure this compound and check what is the rotation, or maybe this rotation is reported. And now you prepare your sample and then measure the rotation, and if you find a rotation a certain amount, and from there you can calculate if there is a 100% purity, this much of calculation rotation, and if I get this much of rotation, what would be the purity? Okay.
Thank you, sir.
So, but that's why there is this sort of error bar, and that's why it is best way to do it with
a reference
HPLC separation. Then there is absolutely no problem.
Thank you, sir. Thank you.
Yeah. Okay, so we got a question from how to improve the. Okay, that's fine. What is the attropisomerism arise? How asymmetric synthesis is done? Attropisomerism is basically when you talk about the rotation, based on the rotation and the restricted rotation, right? So if you have it through axis, if you have a restricted rotation, it's just like a binol system, okay, or biaryl system. So there is a attropisomerism. And it doesn't matter, asymmetric synthesis doesn't follow which isomerism, which chirality, whatever it is. Asymmetric synthesis tells you that if this molecule is chiral, we should be able to prepare in one form in excess than the other. Okay. Please explain background reaction again. Okay, I can explain what is the background reaction. So background reaction means let's say you are doing a reaction. Let's consider that you are doing esterification or acetyl formation or acetylation, whatever it is. You need a little bit of acid. Okay. Now, if this acid is chiral acid, then obviously you will get an induction. Now you check carefully, if you don't add acid, there also a little bit of reaction, let's say 10%, because this is so reactive. For example, if you make acetal, if you do not use acid, you just put it in dense stack, heat it up, you can see some reaction, because you just have to remove the water. And again, it's a nucleophilic addition, water elimination process. So the reaction is happening without acid or with the other acid which is present in your system, just like a little bit amount, like if you add molecular sieve, that can also do some reaction. Okay, so if that happened, that will also deliver the same product. Now once product is formed, see, the one is coming through catalysis and there is an induction, other is coming from without catalysis and there is no induction, so that will be racemic, right? So this is the background reaction, so which is happening without the help of catalyst, and there is a racemic formation. Okay, racemic product formation, and that will reduce your enantiomer induction. Okay, fine. So any other queries, any other question from student?
In between, I have one more question, sir.
Sure.
Sir, in your organocatalysis, sometimes non-covalent interactions are involved to stabilize the transition state or intermediate.
That's right.
So what should be the actual terminology, whether it is organocatalysis or supramolecular catalysis?
No, it is organocatalysis, because organocatalysis doesn't tell you have to go for covalent interaction or non-covalent interaction. Organocatalysis tells you that if you can do catalysis with a organic molecules, and if the active part of the catalyst is organic molecules. For example, there is a we call organocatalysis where we have metal ion in the ferrocene. If you see the Greg Fuchs catalyst I had during my presentation, so I think can I go back to my presentation? I think so, right? Can you see my slide now? Is my slide visible?
Yes.
Okay, so yeah, I think it's a good. Yeah, look at this. Can you see this green structure? This blue, this one. Can you see the slide number 13?
Yes.
And can look at this. This one, this molecule, this ferrocene type molecules. This is Professor Greg Fuchs developed this one from Caltech, and this is a very nice nucleophilic catalyst, and all the reaction is happening from this nitrogen, because this is a pyridine, right? DMAP based catalysis. It is extremely electron rich, just like pyridine, and every reaction is happening here. No metal ion has no role to play. So therefore, even though this one we called organocatalyst, okay. If metal ion is innocent, then we can call organocatalyst. And organocatalyst never says this kind of interaction should be there. Any form of interaction can do it. Okay.
Thank you.
Yeah.
More question from the students?
Yeah. Any other queries? Questions you want me to answer? In case of beta decay, there is a rotation of plane polarized light. This is a nuclear phenomena. Then how can one define chirality? Just by looking at the spatial orientation of bond and group around one central atom. No, I mean, you are absolutely right. See, it is not possible to just say the chirality looking at the spatial orientation. For chirality, you have to, in order to say chirality of any molecules, you have to basically look for the behavior of chirality. You have to find out the behavior of chirality. Just like, for example, if the molecule can be separate in HPLC, it may not be separate also. So this is one way. The other way, of course, if you throw another one sense of chiral molecule and you make a diastereomer. So we call this is the NMR shift reagent. So you provide that reagent and you make a diastereomer and you check the NMR. And if the diastereomer will have different NMR compared to enantiomer. So there are different checkpoints by which you can do it. But for simplicity, we tell students, because this chirality subject is so complicated. I mean, and you need a visualization, a three-dimensional visualization, which is quite difficult. And that's why, with just simplicity, we talk about this one. But you are absolutely right. There are cases which is a nuclear phenomena. That's right.
Any more questions from the students and also from other participants also? There are faculty members from various colleges. Please, you can ask questions. Okay, if there is
Okay.
no more question, I would like to request our head of the department. Okay, one more question.
Yeah. Plane polarized may also be changed in Raman scattering. Oh, well, I mean, I'm not expert on this area. I think I think I won't be able to comment on this because I have no idea about Raman scattering and I don't deal with that one. Yeah. So could be. Thank you.
Any more questions? If
so-called achiral molecule can do that. Achiral molecule can do what? Achiral molecule can do plane polarized light rotation. That's what you said. I don't understand. Sorry.
okay, if no more question, I would like to.
If you have something, this one you may drop me email so I can.
Okay. I will share your email with you.
Yeah, just share my Gmail ID. Okay.
Okay.
So joyramguin@gmail.com. So
okay. I will do that.
So maybe I can just write it here.
Yes. Okay, if there is no more question, I would like to request our HOD, Dr. Angshuman Bej, to give a vote of thanks. Please, Angshuman, please.
Good afternoon to all. On behalf of Department of Chemistry, Jhargram College, we are extremely thankful to our distinguished speaker, Professor Guin, for his interesting, inspirational, and motivated talk about the concept of chirality and asymmetric organocatalysis. I wish to express my sincere gratitude to our Honorable Principal, Dr. Devnarayan Rai, for his continuous support and cooperation in organization of this program. I would like to thank our departmental colleague, Dr. Tapas Kumar Abeldar, for his taking initiative to organize this program. I also extend my thanks to Dr. Praveen Mistry for providing all kind of technical support. I am also grateful to all our departmental colleagues, my beloved students, and all participants, including esteemed colleagues from various departments of our college and also those from other institutes. Finally, thanks once again to all for wonderful cooperation. Thank you to all.
Thank you.
Thank you, Angshuman. Thank you. With this, we are concluding this session.
Thank you very much, Tapos.
Thank you.
It's a great.
Thank you, sir.
Thank you, Angshuman. It's a great pleasure interacting you people. It's very nice. So if